Good evening, ladies and gentlemen. It's been a long day. Thank you all for staying for our presentation. My name is Michael Lasik. I am the lead engineer for this project. I am joined by Noah, RJ, Cam, and Sam. We are the Imperial Abort Gate team. So first and foremost, Imperial is our sponsor for this project. They produce high-end dust collectors for manufacturing facilities across America and then some. They don't just produce the collectors themselves, they also produce the filters for it, disposal drums, basically everything that goes into the system. These collectors are essentially a giant machine shop's version of the filter you put into your own furnace at home. So to give an idea of what the filters are like and what the systems are like. So Imperial produces all sorts of products. Specifically, we are looking at one of these aftermarket parts, high-speed abort gate. So what is a high-speed abort gate? It's actually a safety feature included into a air handling unit system. So the air handlers themselves, the filter and everything, would actually occur on this side of the abort gate. And what happens is because those are a lot of paper, very flammable, and a lot of air is moving through, the abort gate is used as a safety feature that if there's a spark or a flame or some sort of unsavory explosion, it is meant to help redirect the air and allows to prevent the clean air that's coming out of the filter to direct that away from any life or the facilities. So this is actually a brief video that will give a better explanation of how an abort gate functions. So you can see you actually have your spark detection and it'll go through. So when it's armed, there's a door that gets raised and clean air is allowed to move through perfectly fine. If it detects there's an explosion or a spark or something, it gets redirected out. Now, our project was not to redesign the abort gate in its entirety, but primarily the reset mechanism. As you saw, that door had to get lifted in some way to be armed, and so our job was to do that. The parameters overall. So the abort gate closes in less than half a second. We needed to make sure that regardless of how we designed the reset mechanism, we maintained that. We had to make sure it was durable for outdoors. Imperial develops theirs so that their units, the actual reset as well as the control boxes, which you can see there, can go on both the left hand or right hand sides. It has to be scalable from 18 inches, so that door that's swung up, that can be as small as 18 inches all the way up to a 60-inch square door, so they can be huge. Ours was a 18, 20-inch model, but our biggest design goal was we wanted, or they had asked us, to reduce the overall cost of the product, make it cheaper as well as more efficient to build. I'm now going to have Noah speak on the safety and start to get into our actual design.
So first I'm going to discuss safety. When dealing with a piece of equipment like this, it's always better to keep a safe work environment, make sure no one in our group is hurt at all throughout this whole process. Like Mike said, this door closes in half a second, so whenever we were testing this piece of equipment, we always made sure that everyone was a safe distance away so nothing was caught in the door or no one was going to be in the door's path when it dropped. We always wore protective equipment when drilling and modifying this piece of equipment, and whenever we were observing the interior of the actual mechanism lifting the door, we always made sure that we were a safe distance away in case something broke. Like, we added a welded bolt onto our design, and Luke over here recommended make sure you're just a safe distance away in case something failed or miscalculated. And then when dealing with all electrical stuff and rewiring to make our winch work, we had to make sure that our unit as a whole was unplugged from this so that no one was touching live wires and going to get electrical shock when operating on this. And then when making sure all the connections and everything were actually good, we always made sure that no one was touching these live wires to reduce the risk of injury. So the original design by Imperial Systems used a ball screw actuator. This is a very effective piece of equipment, and it is very efficient. But the main issue is that these are very expensive. This actuator actually has a screw that drives the arm, which is able to lift the door to its upright position to the magnet. But the main problem, as I mentioned, is this can be very expensive. And as Mike mentioned, these doors can get up to 60 by 60 inches, which is a massive door. So the heavier the door, the more expensive the actuator, which was definitely something that they were wanting to get rid of. Another thing that they had issues with is their tolerance stack-up issue. Some parts didn't quite align perfectly, so with this part right here, actually, they utilized this screw to reduce the effects of the tolerance stack-up so that the arm was actually driving at the precise spot that it needed to make up for any effects that were caused by the assembly. So overall, this was a very effective and it worked, but we were just modifying it to make it more easily assembled and work just as efficient. So then before we get into some of the ideas that we obviously had to find out how much force we actually had to create to lift this door. So on the previous slide, there were these 3 springs on the arm. We first found the spring constant for these springs. So the top spring is going to stretch the least, the bottom spring is going to stretch the most, which means the most force on this arm, so the most torque to overcome. So we got the spring rate to be around 20 pound-inches, which is very reasonable, and then we calculated that the actual max torque was around 250 foot-pounds that we had to create to be able to lift this door. So then we calculated that the winch force used for this would have to be around 187.5 pounds, and this is with block and tackle, which we'll go into further. So when going into the brainstorming stages, we had a couple ideas, and then we were able to narrow it down to 3 main ideas that we wanted to build off of. And the 3 ideas were the chain and sprocket drive, the winch and pulley, and then the pneumatic system. So first, with the chain and sprocket drive, the idea was to have a motor mounted at the bottom of the box and then have a chain and sprocket, and then the sprocket would actually be mounted on the center shaft, which is pictured right here, and it would allow the slot would push the door up and then would be able to slide out of the way for the door. We thought this would be an effective idea, but then going down to things, we kind of just scrapped it. Because our next idea, the winch and pulley, actually is what we more liked. Because the winch and pulley essentially is a geared down motor, which is what we were initially getting at with the chain and sprocket drive. So we thought mount the winch at the bottom of the box, run a cable to a pulley, and then mount it to the existing driving arm. We did modify this in retrospect, but this was still our initial design in the early stages. And then the last was our pneumatics idea, which was a very good idea, but it was too simple to Imperial's pre-existing idea. This was utilizing an air cylinder and piston to be able to drive the arm up. And Imperial liked the idea, but it wasn't getting rid of their tolerance stack up that the winch and pulley did with its simplistic design. Next, I'm going to pass it off to RJ, who's going to discuss the new parts for this design.
Hi, like Noah said, once we narrowed down our idea and decided to go for the winch and pulley, we needed to create new brackets and new mounts to go inside the box, because in our new design, everything had to be pushed back a few inches, so none of the previous brackets that we have here would work. So first off, we needed to get a winch. Like we said, we were replacing the ball actuator screw, and we had a few different ideas for that, which we'll talk about later. Next, we had to create a pulley mount, a new push arm, and a spring mount. So when we were deciding what winch to use, we had 2 ideas. We had a 110 volt winch and we had a 12 volt winch. Last semester, when we were first narrowing down our ideas, we originally thought a 110 volt winch would be best, because this would be easier to wire into the box, because we could use it directly plugged into the wall, and we thought converting the voltage from 120 volts to 12 volts would cost too much money. But this semester, once we came back, we realized that it would be much more affordable than we first thought. And the benefits with a 12 volt winch is that they're much smaller and much more powerful. And like Noah said, we only had to use 187.5 pounds to pull up the door, and the small winches that we found about 90% cheaper would pull 2,000 pounds single line and 4,000 pounds once block and tackled. So that's why effectively we went with a 12 volt winch. Next, we had to create a new winch bracket. This is the previous bracket that was installed in the box for the ball screw, and as you can see, it's much smaller. But with our new design for the winch is much larger. So that was our main problem in designing this. As you can see, our space was limited, so the main design problem we had with this was fitting inside the box. It's buttoned up all the way to the left side of that screw you can see there, and none of those could be moved in our current design. So, in order to do this, we had a part that was bent with ribs on either side and 4 holes along the bottom to mount it. The only additions we had to make to the box in order to mount it inside was screwing these 2 left holes in because the far 2 left holes were already there previously for the ball actuator screw. Overall, this design was very effective for Imperial because it used the same bend radiuses and similar ideas of the ribbed parts that they had before. So it was very easy for them to manufacture and assemble. Next, Cam's going to talk about the next 2 parts that we designed.
So the next part that we needed to design was a pulley bracket. This pulley bracket effectively changes the direction of force from the winch. So as we said, the winch sits in the bottom of the box, so the force is initially vertical, but we needed to change the direction of pull to be more up and to the left in order to drive the arm. We used a pulley to do this. You can see this piece utilizes a 2-part design, so the 2 halves of the piece are actually laser cut and then bent in the press brake and welded together, as you can see up top. This piece has 4 mounting holes that mount to the back of the box, as well as a hole in the middle for the shaft to go through that the pulley sits on. That shaft in the middle was far too wide for the pulley that we were using, so we had to implement putting spacers on either side, as well as these large discs that you can see here that keep the pulley cable from slipping off of the pulley, the winch cable from slipping off of the pulley. You can also see that we attached this eye bolt at the top, which we then run the winch through the arm and back and hook it to that eye bolt to utilize a block and tackle system which effectively doubles the force of pull on the arm from the winch. We also had to redesign the push arm. So the original push arm that they were using is this piece here. You can see this is a 3-piece design, 2 arms and the hub. We removed this part and we slid the hub forward to allow this arm to align better with our new push arm, which I will cover after. So this is the new reset push arm that we designed. This was inspired by the old driving arm, which utilized a dual arm design with a hub in the middle and this L-shaped piece on the side. So what we kept from that is the dual arm design. However, we replaced the hub with a cross-shaped piece in the middle. This piece sets the spacing right each time, and also the T's on the cross piece act to push the driving arm into place. You can see there is a hole in the bottom for where the pulley shaft sits for our secondary pulley before it wraps back up to the block and tackle on the pulley bracket. You can also see in the top that piece sits on the shaft but is not keyed to the shaft as the driven arm is. The driven arm is driven and keyed to the shaft to rotate the shaft up into place, and then this arm is able to rotate back out of the way. Might be a little bit hard to picture, so I will go through what we actually have in the box. This is our full assembly. So you can see the winch with the winch bracket at the bottom. The winch cable goes up through our pulley mount, which changes the direction of pull, over to the new driving arm, runs through a pulley here. It is then attached back again to the eye bolt at the top. You can see the T-piece, which is pushing on the back of the driven arm, as well as the fact that the driven arm is keyed to the shaft. Whenever this rotates up, this piece stays in the up position as the door is grabbed by the electromagnet, and this spring allows this arm to be pulled back into place as the winch is run in reverse. This gets this arm out of the way until the door is triggered, the power is cut to the electromagnet, and this door is able to swing back down to this position. Having said that, I will now pass it on to Sam to go over the FEA on our components.
Hey, so a little bit about what FEA is before I get into our results from it. FEA is a acronym for finite element analysis. It is a way of using a computer to analyze the stresses and strains inside of a part at many points all at once. It solves thousands of equations simultaneously in order to determine all of the points of motion in the part and the stresses related to those. So with this, some of the parts were a little more challenging to assess than others. We set for ourselves a goal of a factor of safety of about 1.5. We wanted to exceed that with all of our parts on a force scale of 300 pounds in the cable in case the pull is past, in case we pull beyond where the door hits the electromagnet and cannot go any further. If we add extra tension, we could reach 300, and we want it still 1.5 factor of safety before it releases if there is user error in that way. So using that, we analyzed all of these parts that we were replacing in there. This was the most complicated part to test, as it is a dynamic part and not a static part. So a mathematical model, had to be devised that simulated the forces on it. It rotates freely about this shaft, but is constrained by the force of the driven arm as its rotational constraint. Force is applied through these holes as the pulley pulls on the part. Other parts were constrained and forces were applied based on mounting points. So the winch bracket, where the winch pulls from it and where it is mounted, were constraints that were used. The parts all passed with at least a factor of safety of about 1.89 in the case of this part, and all of the others had over 2 for their factor of safety. We had to make electrical changes to the electrical control panel for this design because we switched from using an alternating current powered ball screw to a 12-volt DC winch, which has some challenges in that we needed a power supply which could convert from the 120 to 12 volt with sufficient current, and we found one that did not cost too much and was able to give us 12 volts at 50 amps for about 600 watts maximum power output. This was plenty more than what we needed, and so was what we used. We had to wire it into the AC control panel and then put its output to the winch. We could not use the original raise and retract buttons, so we had to use the winch buttons and install them into the control panel. So this gave us some benefits future down the line when this entire control panel is redesigned for the production version. Many of the sensors are run on 24 volt DC, which is much closer to 12 volt DC than it is to 120 volt AC. So running a 12 volt winch is much easier than running a 120 volt ball screw, and the conversions to sensor synergy is easier. And now Mike will tell you about our recommendations and future iterations.
So we made a number of changes to the abort gate, and they're still not completely done. One thing we did, and we definitely advise Imperial to do so, is the winch we got is a standard like ATV winch you can find at Harbor Freight. What we would recommend they do is work out a deal to have that custom designed so that it would have the exact length of cable, the exact specs, the exact connections, so that they aren't with all this extra items. I mean, ours came with way more cable than we needed in any capacity. We had to rework the entire control system slightly, at least mechanically, by integrating it into the box. Some of the parts that we have designed, we've already started looking at ways to improve upon those. The pulley bracket, which had the eyelet welded to it through some nuts, we would be mechanically adding that in by designing that directly into the part itself instead of having to mount that, as well as some other minor changes to make it just more manufacturable. So our goals, again, was to make it cheaper, which we did significantly. If you were to assume that all the parts, all the sheet metal pieces were one-to-one from what we removed and what we put in, and the only financial change is going from the ball screw to the winch is somewhere between 90 to 96% cheaper than the cost of the ball screw. And it's a significant decrease. We can't speak much more to money on that because there is a very high likelihood that this will be Imperial's new product, so that we will see it get moved into full production. With the way we still kept the original springs for the door, it still meets all the same safety factors and design factors and durability of the original. And we even have now made it more compatible electronically by switching to the 12-volt DC winch. We now have a video that shows both the original system functioning as well as our updated system, and then a side-by-side comparison so that if you didn't get a chance to see it earlier today, we can see it. It's kind of bigger. We would have brought it in ourselves. So with this starting, this is the original design. As you can see here, the ball screw is raising and it's being pushed up there via the bolt, and the springs are stretching. And what you'll see is once it hits that max point, the magnet has then attached and it's bringing the ball screw back down so that when the door is dropped, it's not fighting to come back down. Now here's our design doing the similar thing. Instead of the bolt, our push moment is right there. And you can see us bringing that back down after the magnet has connected as well. So you can see ours is actually faster. And so here is a side-by-side comparison between the two different designs to give you just an overall idea of how both systems have worked and changed. I want to thank everyone for their time. I want to give special thanks to both Imperial for their support through all of this, for actually helping fabricate parts of our parts. I also want to give a big thank you to the Grove City Machine Shop, Luke, Jim, Miss Henley. All of you were amazing in helping us get all the other things that we needed done. I want to thank everyone here for watching. I want to thank Dr. Yu for being very helpful in advising and giving input and helping with things. And I would like to open the floor to questions at this time.